Okay, now we're ready to talk about the Viterbi algorithm. So this is an offline algorithm as opposed to the Bayes filter, which was an online algorithm. So the Bayes filter, we get a new measurement, and right then and there, we can update the probability distribution over our state space, given the new measurement. The Viterbi algorithm has a slightly different goal. It says, given all measurements over all time. So I'm not doing this real time. I'm recording this stuff. I'm recording it all. And I'm going to come back to it and look at everything. So given all measurements over all time, compute the sequence X. So I'll say, that's a sequence through the state space over time. I'll say maybe it goes up to time capital T. So compute this sequence of states that maximizes the probability given all of the measurements. All right, so we're going to use the same observation model and the same transition model that we did for Bayes filtering. They're problem specific. These are things that I'll define depending on the problem. So, my observation model for the robot was based on the scans being similar to the idealized scans, and my transition model was based on going to the neighbors, but depends on the problem. Okay, but so given those, here's another thing I can compute other than the belief. I can actually compute an overall sequence through the state space over time. Okay? So just to write this as an equation, I would say I'm trying to find x is equal to argmax, maybe I'll say x prime, argmax x prime of the expression probability of x prime given all the observations, y0, y1, all the way up to yt. So this is what I'm trying to solve for. This is my goal. I would love to find the sequence that maximizes this probability here. Okay. Now, unfortunately, naively, this is not going to work out too well because, there's an exponential number of paths. So if I'm looking, so here's the state space, and I'm trying to go over time. So maybe I'll index this a little bit differently here, and I'll say, okay, still the rows of this are going to be the states. The columns are going to be time. But maybe let's say, okay, this here is time 0. This is time 1 here. And then maybe, we have a dot, dot, dot. Mathematicians could never get anywhere without the dot, dot, dot. So we have a dot, 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 and then at some point we're up to t minus 1 here. Actually, let me move this over too. We're up to t minus 1. And get that k over there. And then here we're up at t. So, what we're trying to find here is a sequence of states that maximize the probability. Well, maybe I'll highlight a couple here. So maybe I chose that state, and then maybe I went to that state, and then maybe I went to that state, and maybe I went to that state, right? So there's one possible path. Boom, 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 boom. But that's only one of many possible paths. I could have branched out in a different direction. Maybe gone here, and then here, and then here. Or maybe I did this, but then I changed my mind and went here, and then I went up here. So there's a lot of different paths that I could do. And so if I was going to come up with a naive algorithm, I would just try all possible paths, and then I would see which one gave me the maximum probability here. But the problem is, the number of paths is, it's the number of states. So here it's 6, raised to the number of time steps that you have, which, if I'm 0 indexing going up to t, is t plus 1. So here it would be 6 to the 4th, which is not too bad. But let's say I wanted 20 steps, and 20 is really not that huge of a number. But if I only had 6 states, 6 is a puny state space, only 6 states. Okay, this is how many possibilities I'm going to have to consider. Not very good. But luckily, our saving grace is like the dynamic programming problems that I just showed you. These are seriously overlapping. All right, so they're overlapping. And they're also independent. So guess what? We can use dynamic programming. But to see how, I need to write down a recurrence. Okay, so just like I did with the Fibonacci sequence and dynamic time warping, I need to write down some kind of recursive relationship of some kind. Okay, so let me define, so let L at state J time T. Okay, so row J, that's the state, the column is the time. Let this be the maximum, or the probability of the maximum likelihood sequence that ends at state J at time T. Okay? So here's my subproblem. I'm saying, okay, let's suppose that I was able to solve this problem up to time T if I made you end on state J. Okay, that's a subproblem. I'm insisting that you end at state J, and I'm considering the first T states. All right, so here's what we can say. So now we have the following recurrence. LJT. Well, I kind of have to draw a picture to show this. So let's say, all right, so here I am at, so to avoid confusion, let me get rid of these for a second. So let's say that I am at state J. Okay, let me get my letter here. Let me get that J in this state here. So let's say that I'm at state J. I could have, just like before, I'm using the same kind of reasoning. I could have come from any state at time T minus 1 if I'm at state J at time T. And the probability of doing so would be given by the transition model. Okay. So what I can do is, I'm thinking recursively or inductively here. So let's assume that I already have the solution to all of the subproblems at T minus 1. And what I'll do then is I'll look and I'll see, okay, let's look over all the subproblems at time T minus 1. So let's look over all of them. And let's see, okay, I have the solution. I know what the best, the cost of the probability of the best sequence would have been to get from the start up to this particular place. So who knows what it actually was? It was going all over the place. It went all over the place, and then it settled here. And somehow I've computed that that's the best path and that's the best solution. That's the probability of it. And so what I can do is say, all right, I know how to do that, and now I just have one more step. I'm insisting that you end up in J. So I'm simply going to multiply by the transition probability of ending up at J. So we have, looking over all possibilities of where I could have come from, the cost of the best path to get there, the probability of the best path to get there, well, that's going to be K T minus 1. So I have that subproblem. That's neat. Times, okay, I'm tacking one more on here. I'm tacking one more path on the end. That's going to be the probability of xt equals j given xt minus 1 equals k. All right, so I just multiply the accumulated probability to get here times the probability to get there. So it's starting to look a lot like A star in some ways. There's a lot of analogies here. So that's great. That gets me the transition. But actually, just like Bayes' filter, I have to then multiply that by the observation probability. So the probability of observing y at time I, given that we're in, time t here, given that we're in state J at time t. Let me get this out of the way here. Okay, so that's my recurrence. So I look and I see, okay, what are all the possible states that I could have come from? What was the best I could have done to get to those? Let me accumulate this one additional hop here. And once I found which one is the best, which one minimizes that, I'm going to multiply that by the observation probability at this new state that I'm adding to my sequence. All right? So that is the hardest part. We've gotten through the hardest part. The only thing I need to do now is look at the base case. So what you can do is, all right, look, at the first time there was really no observations or anything. So what I'll say is L at J, I'll say -1, so before time even starts. I mean, this can be whatever you want. So this is just the prior probability of J. And I'll do the same thing in the robot application that I did with Bayes filtering, and I'll make that a uniform distribution. So I'll make that an equal probability over all the states. The other thing I want to be sure to do is I also, like I was doing with dynamic time warping, I want to remember what the best state was. So I'll define another matrix called B, which instead of the min, it's going to be argmin. And actually here I don't need to tack on the probability at the end because that's not going to affect which one of these minimizes. So let me actually remember which was the best one that I came from. And then I can do backtracing. Okay, so we we have our equations for Viterbi now. And it's going to be a heck of a lot better than exponential, because just like dynamic time warping, we're just filling in a table. This table has as many rows as there are states, and it has as many columns as there are times. So it's number of states times number of times, potentially also times the number of states, because for each one of these I have to also do another loop. So really it's a triply nested loop, actually just like the Bayes filter was as well. So, okay, so let's pause for a second. Let this sink in, and then we're going to try to code it. Okay, let's try to code this up for the robot problem now. So, as promised, I have two two-dimensional arrays. One of them is called L. This is going to hold these accumulated probabilities of the best choice I could make to get up to a particular state at a particular time. B is then going to hold the best choice of where I came from before that. I'm going to make sure that this is integer typed just like I did for dynamic time warping. First thing I'll do, I'll set up the initial conditions just so I don't have to deal with any out of bounds errors. So this is kind of dealing with the base case here. I'm saying, all right, look, the base case, everything's equal. That's what I decided, and I'm just going to tack on the first measurement probability here. So what is the measurement probability of my first observation given every state, and I'll remember that. Whoops, I flipped the indices here. That should be, this is, oh no, that's right, state k times 0. Okay, good. So I have that. Now what I'm going to do is I'm going to loop through the table in order of time, and then I'm going to fill through each one of these columns. So let me go back now. And okay, so I'll say for t in range 1 up to the last time. Now what I want to do is loop through every state j. So let's say for j in range num states. And again, so now I'm going to consider every state that I could have come from, and I'll do a similar kind of thing to what I did before, where I only consider the state that is actually within one hop of where I currently am. So there's only at most 4 possibilities of where I could have come from. It's either left, right, up, or down. And here's the probability of transition, which I need, right? That's this probability here. So what I'll do is let me try to figure out, I'm trying to maximize the probability. So maybe I'll say, the max is equal to 0 until proven otherwise. The probability here is going to be, so the probability of transitioning from K, it'll be that times the best I could have done at state K at time t minus 1, right? So it'll be that times the probability of transitioning. And so if that probability is less than the minimum, or if that probability is greater than the maximum that I've seen so far, then I'll reset the maximum to be this probability. And you know what? I'll also go ahead and I'll remember in this B matrix, so I'll say B at state J time t, I'm going to make that equal to K. So remember that K was the best that I came from. All right? So that's this part here. So I'm looping through. So I'm looping through all K. So min over all K, where I could have come from. Compute the subproblem. So look up the subproblem of K at time t minus 1. Multiply that by the transition probability. And we're trying to find, of course I should have said max. Oh, one little mistake I made. We're trying to maximize a probability here. Okay, that's an important thing. So maximize the probability. So that's why I start off with this being 0. And then I'm looking for the subproblem that maximizes. I'm looking for the maximum likelihood sequence. Oops. Okay, one little mistake that I made. Okay, cool. So we've got that. Once we figured out what that is, we can finish here what the final probability is. Well, I might as well just put it right in there. So I'll say, okay, I can actually compute now L at state J time t. That's going to be whatever the maximum transition probability was times the observation probability. So what I need is again, the get measurement probability of state scans at index J. So given that we're in the state where we ended up, what is the observed scan at time t? Okay, so now there's one little thing I sneaked in here that I need to change compared to the Bayes filtering. So we're going to be multiplying a lot of tiny numbers together, and that will quickly underflow. So just like we did with the naive Bayes when we were doing bag of words and we underflowed there, what we actually have to do is switch to log probabilities. So I'm actually going to make this be a log probability that I'm storing instead of a straight up probability. So I have a little flag for the measurement probability that'll return the log. I just need to then update this instead of times to be a plus, because when I take the log, it turns into a plus. So before, maybe I'll keep that there in comments, what it used to be. That's what it used to be. But now when I take the log, it's going to be whatever the sum of the logs was up to this point plus the log of the transition probability. And then we're going to add on the measurement probabilities log down here. Okay, so that should be everything I need to fill in L and B. So before I do anything else, this is some code I have to plot the result when we're done. But let's just make sure this code runs. Okay, good. It seems to have run. Let me make sure that L looks like something that's not just complete garbage. In fact, I can plot L, I guess, to look at what it looks like. Okay, so I'm definitely seeing one region of the state space is definitely more likely than others over time. Does that make sense? I mean, well, I guess it depends on how the states were ordered. But, all right. Yeah, let's see. We'll keep going. So let's now do the backtracing. So what I want to do is find the last state that has a maximum accumulated probability. So I'll start with my state J being argmax of the last column of L. So it's like, okay, I'm at the end. Which one of these actually ended up on the best path? Let me start the back tracing there. And now I'll say, while J is greater than 0, I will simply follow the arrows that I remembered here. So let me say path is equal to J. So I'll say J is equal to B. Oh, and I should also keep track of what time I'm at here. So actually, maybe I'll make the time start off at the end, so that'd be t minus 1. So take the one that is max at the last time, and then I will follow that back. So I'll say, okay, what was the best that I did to get here? So, whoops, I switched to the indices here. What was the best I did to get to state J at time t? And now I will also move t along. So I'll keep moving to the left. I'll move from this column to this column to this, and I'll just follow the arrows until I get back to the beginning. And then I'll have my path. So I'll be sure at this point to append my J that I just got to the path. Okay, now this seems a little bit fishy because I only have 2 states in the path. Oh, I meant to say while t is greater than 0. Okay. Okay. That also seems fishy though, because we just jump straight to state 0 and we stay there. So let's see if we could find any problems in the code here. Okay, so I start off with my base case measurement probability. I go through here. Let's check the equation again. So I have this transition probability. I look through all the possible neighbors. I'm trying to remember the one which maximizes the probability. So I'll remember that here. And then I remember the actual probability itself, because that'll help me compute the next column. And then I do the backtrace. Okay, so I'm going to look at this for a second, see if I can find the problem. I found the problem. It's very subtle. Since I switched to using logs, these are going to be negative numbers, unless the probability is 1, which never happens. So what I should do is actually start my maximum probability off as negative infinity. That would be the log of 0. A 0 probability, and that's kind of my lower bound for what I should be getting. Okay, so now, I bet you the image is going to make a lot more sense now too. So if I look at L, okay, well, I still kind of stick up to these states here, but anyway, my path looks a lot cleaner here. So, actually, I guess I called it path, but I expected myself to call it states. So let me just quickly update that. So I'll call this states, and then I have some code down here to plot what the estimated path was. And let's see what we get. Oh yes. Oh, it's perfect. Okay. Yeah. So in the black line is what we know the path is supposed to be because we simulated it. And then this dashed line is what I get from the Viterbi algorithm. And what's so cool about the Viterbi algorithm compared to the Bayes filter is that because you're able to use all of the observations, you can correct a lot of mistakes. So notice, before when I had the Bayes filter, there was a lot of ambiguity and there was noise and sometimes, this little green square here is showing my estimate, and sometimes the estimate wasn't quite where I was actually. So the maximum probability at any point in time didn't necessarily coincide with the true value. Now, I'm not saying that'll always happen with Viterbi, but it certainly does better on this example with a high amount of noise. It might get some bad measurements in the middle, but the overall sequence is able to correct for it. So it's analogous to if you're trying to do voice to speech. Maybe you got some noise here and there. You weren't so sure about an individual phoneme. So the individual observations might be quite bad. But somehow that overall sequence is the most likely thing that could have happened. And it'll power through some bad observations. So this is the amazing thing about the Viterbi algorithm. And even though these are independent and overlapping subproblems, the independence comes from the Markov assumption that we only depend on the state right before us and nothing behind that. That's why we were able to write it in terms of these subproblems. So it seems like, I only remembered where I was before, that's all I depend on. But actually, these dependencies keep going recursively. So when we run through the Viterbi algorithm, we're considering an entire sequence. So it seems like it might be limiting to only relate to the previous state. But actually, overall, when you do this maximization with dynamic programming, you're really able to, this is really a global optimization over the whole trajectory. So this Markov assumption makes the problem tractable. It makes it so I'm able to compute this with a polynomial time algorithm. And it works quite well globally. So I just love this. This is one of my favorite algorithms ever. I use it all the time in my research, and I wanted to share it with you, and you'll be applying it on the homework. So I just have a quick comprehension question to make sure that you're following this. And of course, I will provide this code as a solution so that you can refer to it when you go do something similar on homework. All right, so I hope you enjoyed that. I hope it made sense. Please let me know if you have any questions, and we will check in more about this soon. Thank you for your attention.